Welcome, students. So we will start the next lecture, and we will resume from where we left in the last lecture. So we were discussing about the axioms of the probability theory. So we saw that if we have a sample space which is denoted by capital omega, and if you define an event E that is a subset of that sample space, then the probability of that event E lies between the two numbers 0 and 1. So the event E uh, can be either the entire sample space. In that case, we have the uppermost boundary, which is 1. The event E can be impossible event. In that case, the lowermost boundary of 0 will be occurring as the probability of that event. And in general, for any event E, the probability will lie between these two boundaries of 0 and 1. And if you take the probability of the entire sample space, which is a sure event which is bound to happen, that will give you the value equal to 1. And then if you have mutually exclusive events, E1, E2, E3 and so on, you have this particular relation, which is the union of all the mutually exclusive events, and the probability of that will give you the sum of the individual probability of those events. So by mutually exclusive events, it means that these events E1, E2, E3 have nothing in common between them, or in other words, they are non-overlapping. If you just try to express them by a diagram, then they will show that they are non-overlapping. So an example will be that when you are throwing a die, you have 6 mutually exclusive events, which means that if there is a 1 which is occurring after throwing a die, it is mutually exclusive from the event which says a 2 will occur when you are throwing a die. So 1 and 2 cannot occur together, so that's impossible. So that these two events, they don't overlap, so that means these two events are mutually exclusive. And in fact, all the 6 events of throwing a die are mutually exclusive. So either it can be 1, it can be 2, it can be 3, it can be 4, it can be 5, or it can be 6. And each of the individual probabilities, the value of them will be 1 over 6. So what is the probability of getting a 1 when you are throwing a die? It will be 1 over 6. What is the probability of getting a 2? That is also 1 over 6. So if you take the uniform of all these events, so that means it's basically, in this particular example, the entire sample space. And if you see this expression, from the left hand side, so if you take the left hand side of this equation, then the union of all the events for a die throwing experiment is basically the entire sample space. So the probability of that will be equal to 1. And if you then look into the right hand side of this equation, then this is basically summing up all the individual probabilities. So all the individual probabilities are actually equal to 1 over 6. So you are adding 1/6 6 times. So basically you will get 1 also here. So that's what this axiom 3 states. So moving on with the other properties of the probability measure. So if you define E complement, which is denoted as E superscript C, then that is basically the complement of the event E, and that is probability of that complement is equal to 1 minus probability of that event, and if you add them together then it gives 1. So that means something has to happen. So if, let's say, E is the event of having head when you are throwing when you are tossing a coin, then E complement will be the probability of having a tail, and both of them are half. So this property holds. So probability of E complement in case of tossing a coin is half, and 1 minus probability of E will also give you half. Then you can test this for other random experiments also. In case of throwing a coin, you can say that, let's say, E is an event of having a even number. So the even numbers can be 2, 4 and 6. So there are 3 occurrences of having an even number out of 6 total. So 3 over 6 will give you the probability of having an even number, and that will be half. And if you see the E complement, which is probability of having an odd number, that will be also half, because there are 3 odd numbers that can occur, 1, 3 and 5. So that is also half. So you can test it with any random experiment. Then probability of a null event or probability that nothing has happened is 0, because something has to happen. Then property 3 says that if you have 2 events E1 and E2, so the general rule is that probability of E1 union E2 is equals to probability of E1 plus probability of E2 minus the probability of both of them occurring together. So in case of a mutually exclusive events, as you saw in the axiom 3 of the last slides, this probability of E1 intersection E2, or in general the probability of the events happening together, is always 0 if the events are mutually exclusive. So in that case you have probability of E1 union E2 is equal to probability of E1 plus probability of E2. So basically if you see, let's say this is your sample space, and then let's say you have mutually exclusive events E1 and let's say this is your E2 and this is E1 and then this is your E3. So you see that these 3 events are mutually exclusive, they don't have any overlap. So in this case you will have the probability of E1 union E2 union E3 is basically the probability of the sample space, which is equal to 1, and this is again this entire sample space, since it is made of these 3 regions. If you sum up the area of these 3 regions, you will get the entire sample space. So intuitively saying, this is basically the probability of E1 plus probability of E2 plus probability of E3. So this is true for any mutually exclusive events, but however if there is an overlap of these events, then you have to subtract the probability of the overlapping region. So I can demonstrate this with another picture. So let's now assume that your E1 is this one and your E2 is this one, and then you have this overlapping space, which is basically E1 intersection E2. So if you want to have the probability of E1 union E2, so E1 union E2 is basically this entire two circles together. So let's say E1, let me choose a different color. So let's say your E1 intersection E2, sorry, E1 union E2 is this entire red shaded region. So that is basically the individual, if you sum these two circles, first the E1 and then E2, so basically this region appears twice in that sum. Okay, so you can say that probability of E1 is basically so basically probability of E1 union E2 is this entire red shaded area, and you can see that if you sum the individual probabilities P1 plus P of E1 plus P of E2, then you end up adding this shaded area twice. So then you have to actually minus or subtract the shaded area, which is actually E1 intersection E2 once from the entire equation. So that way you will get the entire red shaded area. So, and then you can extend this concept for many events, E1, E2, E3, and so on. So so having said that, let's move to the original slides. So let's say so we have this property 3, and I have explained just now how this is happening, and you can extend this for any number of events, E1, E2, E3, E4, E5, any number of events, and you can find out the relationship by drawing a diagram as I just show. So for 2 events, this is the relationship. For 3 events, this will be different, and then that will directly come from the diagrammatic representation of those events. So if there are overlaps, you have to carefully subtract those overlaps and so on. And if the events are mutually exclusive, which means they don't have any overlapping areas, then it is pretty straightforward. It's just probability of union of all the events is actually the sum of the probabilities, as you saw in the axiom 3 of probability measure. And the fourth property says that if E1 is contained in E2, then probability of E1 is less than equal to probability of E2. So again, this is pretty much intuitive. If you draw a diagram, you can easily find that if E1 occurs completely within E2, then probability of E1 is always less than or equal to E2. The maximum it can be equal to E2. So that's what this expression says. Now moving on with the concepts of conditional probability. So basically if you are observing 2 events, and if occurrence of one of the event has some relation to the occurrence of another event, then the knowledge that E1 has occurred changes the probability of E2 occurring. So this is true when the 2 events has some relationship or one is related to the another and vice versa. So let's say if your probability of event E2, like E2 has occurred before, and probability of, the event E1 has already occurred, and you want to find out what is the probability of event E2 given that E1 has already occurred, and that is actually represented by saying probability of E2 given E1. So this is the way to represent that. So probability of E2 given E1, and this is called the conditional probability. That what is the conditional probability of E2 occurring given E1 has occurred. So let's say let me give an example. So again, take the experiment of throwing a die. So you want to find out, let's say E2 is the probability of getting a 2. Okay, probability of E2 is basically probability of getting a 2. Let's say let's assume, and let's assume that E1 is the probability of getting a even number. Okay, so if I say that E1 has already occurred, if I say to you that it is an even number, then what is the probability that that even number is 2? So that is given by probability of E2 given E1. So basically, what is the probability that I have got a 2 while throwing a die, given the information that it is an even number? So in that case, if you see what are the even numbers that can occur when you are throwing a die, it will be 2, 4, and 6. So there are only 3 possibilities. When I say beforehand that an even number has occurred, your observation space reduces. Out of 6 possible outcomes of throwing a die, you can immediately rule out 3 of them, and you work with just the 3 even numbers. So 2, 4, and 6. So out of these 3 even numbers, what can be the probability of having a 2? It will be 1 over 3. So that's what is given by this expression. So if I say this is what is the probability, let's say E2, let's say this is the event of getting a 2, and let's say E1 is even number. So just trying to map the example with the theory. So in that case, as I just say, so when you know that it's an even number, it's basically 3 possible outcomes are possible. So that is 3. And what will be the possibility of having a 2? So 1 out of these 3 will be 2. So that's the probability, 1 over 3. So now if you look from this perspective, this expression's perspective, so probability of E2 given E1. So what is probability of E2 given E1? So basically, probability of E2 intersection E1. What is the probability of E2 intersection E1? So E2 is the number 2, E1 is even number. So that probability is 1 over 6 in case of a die. So it is an even number and it is 2. Together, that is the only one possibility is there. So that probability is 1 over 2. 1 over 6. And what will be the denominator? Probability of E1. So probability of an even number occurring in die throwing experiment. That is, there are total 3 possibilities, and then out of 6 you have 3. So this denominator probability PE1 is 3 over 6, and then this will give you 1 over 3 as well. So this is how you can calculate conditional probabilities. Basically, if two events have some relations between them, then you can calculate the probability of one event given the information the other event has already occurred. And this is the equation how to calculate conditional probability. And there is another case, this conditional probability of 0 will be 0 otherwise. So there is also a condition here, like this equation holds true if probability of E1 is not equal to 0. Otherwise this will be 0. So so now there is a case that if probability of E2 given E1 is equal to probability of E2, so that means E2 does not depend on your observation of E1. Whether E1 has occurred or not doesn't affect the conditional probability. So the conditional probability of E2 given E1 is same as the probability of E2. Or in other words, probability of E2 given E1 is equal to probability of E1 times the probability of E2. So then if this condition holds, then we say that E1 and E2 are statistically independent. Okay. So moving on, using the relationship of the conditional probability in the previous slide, we can write the Bayes rule as this. So probability of basically E2 given E1 is equal to probability of E1 given E2 times probability of E2 divided by probability of E1. So this comes directly from the relationship in the previous page. So this one. So if you see probability of E2 given E1 times probability of E1 is actually probability of E2 intersection E1. So basically this multiplied by this, if you take this on this side of the equation, so basically this will be probability of E2 given E1 times probability of E1, and this is basically equal to probability of E2 intersection E1 as per the relationship of conditional probability. Sorry. So this is E2 intersection E1, and then this particular expression is also probability of E2 intersection E1. So you can write it in another way. So you can write it in E1 intersection E2 times probability of E2 is also probability of this. So these two are same. Okay. And then depending on whether E1 has occurred first or E2 has occurred first, you can interchange the relationship. So both this and this will give you the probability of the intersection of the two events E1 and E2, and then you can write Bayes rule like this. So this is a very important expression in probability theory, and in your digital communication module you will be using this rule many a times while you will be calculating the probability of error in the receiver, or in information theory when you will be calculating the information and entropy. You will be using a lot of this conditional probability and Bayes rule. So moving on. Okay, I'll skip this exercise and I will leave it to you for homework. So let's move on with the other theories. So let's say the total probability theorem. So let's see what is it. So let's say if we have some events E1, E2, E3 up to En, which is denoted by this. So EI, I running from 1 to N, and union of all these events gives you the sample space, the entire sample space, and intersection of any two events EI and EJ gives you the null set, which means that these events are mutually exclusive. So this actually implies mutually exclusiveness. So they don't overlap, or they don't have any commonalities between them. So in such a case, if for an event A we have the conditional probabilities, probability of A given EI, I running from 1 to N, then PA can be obtained as the sum of this this term. So so PA is basically the sum from 1 to N of probability of EI times probability of A given EI, and this can be easily demonstrated. So let me show you. So let's say so let me just erase this space for you, and let me demonstrate the equation that you just saw. So let's say I have a sample space. Okay, so let's say this is my entire sample space. Okay, sample space omega, and let me partition this sample space into, let's say, some events. So let's say E1, then let's say E2. So these are not overlapping. Okay, remember that any EI intersection EJ is the null set, so there is no intersection between these events. Basically they are mutually exclusive. So let's say this is E4, and let's say this is E5. You can partition it in any form you want. So let's say I have 6 events. So let's say my I equal to 1 to N, as you saw, is 1 to 6. So these are the 6 events that partition the sample space. So now let's say I have my event A. So this blue one is my event A. Okay, so A can be demonstrated, or A can be represented, you see, as sum of these areas. So let's say this is let me start with this one. So this part is A intersection E1. So this is the part of A and E1 that has common. So this is A intersection E1. So basically A, the event A is basically the union. So A intersection E1, this union of A intersection E2. So again, this part, this is A intersection E2. Then this part is A intersection E3. So you can then again write union of A intersection E3, and then you can again write this part. So A, so this is the union of A intersection, E4. So in this way, you can write basically you can write A as the union of I equal to 1 to 6 of this A intersection EI. So you can verify it from this figure basically all these areas are mutually exclusive. All these A intersection EIs are mutually exclusive, they don't overlap. So this is one, this is another one, and this part is the distinct boundary. Then this is the distinct boundary of A intersection E2. Then this is the distinct boundary of A intersection E3. Then this is the distinct boundary of A intersection E6. Then this is the distinct boundary of A intersection E5, and then this is the distinct boundary of A intersection E4. So this A can be represented as a union of all these A intersection EI, and then since these are mutually exclusive, you can write probability of A if you take probability on both sides. So this is basically the probability of union of all these mutually exclusive events, and since these events A intersection EI are mutually exclusive, you can write this as a sum from the axiom 3 of probability theory, that this is I equal to 1 to 6 of probability of A intersection EI. And then from Bayes' theorem you can write A intersection EI as probability of A times probability of A given EI. So basically this can be represented as probability of A times probability of A given EI, and then the sum. So that's what is mentioned here in this slide. So probability of A, if your A can be represented like this, then probability of A can be written as the sum of this. So basically, which I just shown how to write that. If all these EIs are mutually exclusive and any event A can be represented by the conditional probabilities of A given EI. And then I can write the Bayes rule in another form. So I can write probability of EI given A as probability of A given EI times probability of EI divided by probability of A. So this comes from the equation here, this one. So this part comes from directly from Bayes rule, and then you can write PA in the denominator as this expression which we just derived. So this is another form of writing Bayes rule. If you have any event A and then some other events EI which are which are related to A, then you can write Bayes rule in this form.